Hello, Schools of Hope. I'm going to go through some of the organic questions and the answers. I'm going to give you the answers. Your supervisors will have them, but this is a little bit more explanation just in case you're puzzling over some of the answers. So I'm now going to share my screen and I'm going to show you the questions and I'm going to go through what it is that is required in the particular questions. Okay, so here we are. This is question 1. This is the ones called Organic Chemistry Questions 2. In this one here, we've got a student testing 3 chemicals, A, B, and C, and they mix them with water, bromine water, purple potassium manganate. And we've got the results, and what we've got to try and do is to work out what A, B, and C might be. Try to concentrate on just one at a time because it's easy for your mind to go, oh, this, oh, and so on. That's not very useful. So what we want to try and do is to concentrate on only one. Some people cover up B and C while they're looking at A. Let's have a quick look at it. Okay, so if water is added and it mixes easily, this might mean that it's possibly an alcohol, an alkanol, or possibly an alkanoic acid. Let me just do that again. Alkanol or alkanoic acid. And the reason for that is that the hydrocarbons like alkanes and alkenes do not mix with water because they've got different intermolecular properties. Bromine water stays orange, and that means it isn't an alkene. Purple potassium manganate, this is an oxidizing agent. Purple goes colorless, and this means it is oxidized. Now, if it's oxidized, it can't be an alkanoic acid. It's got to be an alkanol. So it's probably an alkanol. In the second one, this does not mix with water. This means that it's probably a hydrocarbon. Sorry, my handwriting is a bit rubbish today. The orange stays colorless. Now, if it's, turns colorless, that means that it's probably an alkene. The purple potassium manganate also means that it's probably an alkene, so it is an alkene. So just try and take it in order. Does not mix, that means that it's not got an OH in or something like that. Does turn colorless, that means it's an alkene. Goes colorless, this also works with alkenes, though you don't necessarily know that. Does not mix, oh, probably a hydrocarbon again. Stays orange, oh, that means it's not an alkene. No change, I don't know what that means here at the moment. So this is more likely to be an alkane, all right? So that gives us an idea of how that one goes. So let's move on. This is explain how you can tell the difference between this chemical and this chemical. If I draw them out very quickly, you'll see that the one above with OH here is very different from this one here. And hopefully you will recognize that this one here is an alkanol. Whoops, alkanol. And this is an alkanoic acid. Now, the easiest way to tell the difference between these two is to spot that this one is an acid. So it says, explain how it could be, how the difference could be told. So we look at this one, and I would say, add something which is going to react just with the acid, not with the alcohol. And that would be something like a carbonate, because all carbonates react with acids. So for instance, sodium carbonate, and it would fizz or effervesce. Doesn't matter which one you choose, and it would actually produce carbon dioxide. If it was this one, you've got to say that would show that it would be this one. Okay, you can't just say, oh, I do that and one of them would fizz. You've got to say it would only do it with this one and it wouldn't do it with that one. Okay, next one. Chemical test to distinguish propane from propene. This is just like the bit right at the top. We'd add bromine. We can write bromine water like this with the AQ, and propene makes it go colorless. Now we should really say from orange. Okay, we should say it goes orange to colorless, but propane, there's no change. Okay, that's important that you compare the two of them. Okay, it's distinguishing the two. So you've got to say what does happen with that one and doesn't happen with this one. Okay, we've got this organic compound, empirical formula HCO2 has a mass of 90. It reacts with ethanoic acid in the presence of a few drops of concentrated sulfuric acid. Now, this should tell you something, this pleasant smell. Organic compound G, whose empirical formula is HCO2. Right. So what we do to start with, we say, all right, this pleasant smell probably means it's an ester, but I'm going to hang on this. So HCO2, well, if I work out the mass of that, that would be 1 and 12 and 2 16s, which is 45. And it says it has a molar mass of 90. In other words, its molecular formula would be twice that. In other words, it's H2C2O4. That's really quite important. Now, it says it reacts with ethanoic in the presence of a few drops of concentrated sulfuric, forming another compound, J. So find the molecular formula of G. We've done that. So we do it simply by working out what the mass would be if it was just that. And then we go, okay, that's, I should have said 90 divided by 45 is 2. Therefore, it's 2 times HCO2, and that makes it H2C2O4. Then it says, to what class of homologous series do G and J belong to? Well, G, organic compound, reacts with ethanoic to make an ester. Then you've just got to go, okay, ethanoic acid, that ethanoic is an acid. So this must be an alkanol. For something to react with it, because basically esters are formed from the reaction between an alkanoic acid and an alkanol. And J, we've already said, is an ester. Okay, next question. Chemical tests to distinguish between two compounds here. What they're doing here is asking you just to try and make sure that you can work out what these are. They're both C4. Then we put the hydrogens round. Let's assume they're all single bonded to start with. This one's C4H10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be an alkane there. Okay, it's not asking me to draw them out, but I think it's the best way of doing it just to start like that. If this one was single bonded, we've got a problem because we haven't got enough hydrogens. If I start putting hydrogens around, 1, 2, 3, 4, 5, oh, I'm going to run out. That means that somewhere in here, I've got a double bond. Now this carbon here will have 1, 2, 3 bonds, so only one more, and this will have 2 here. That's C4H8. Ah, this is an alkene. Chemical test to distinguish between these. That's Br2, orange to colorless, and that does, and this doesn't. So there we are. Same thing, but what you've got to do first is to spot what the chemicals are. Just draw them out. Remember that carbon has 4 bonds. Next question. They're very similar. You see, when you see a lot of these KCSE questions, you'll find the same thing. Ethanoic acid, ethanol. Ah, okay. So that's an ester. Now, the name of the ester, I'll go through in just a moment. Describe how you would know it had been made. That's like that question up a little bit further up. And that's its pleasant smell, often described as sweet. Pineapples, bananas, when they're ripe, mangoes, all of those, they're giving off esters. Now, this actually forms something that looks like this. Double bond O, O, C2H5. For those of you who are interested, This bit is called ethyl. And this bit here is the bit from the acid, and that's called ethanoate. Now it says name the organic product. So this is the proper answer, but I suspect you'd get 1 mark for ester and 1 mark for the pleasant smell. Describe a test the student could use to tell if there was any ethanoic acid left in the mixture. I said these things keep on coming up. This is the Na2CO3. So we'd add Na2CO3 and it would fizz if any acid was left over. Simple. I know this is, if you were writing this big on an exam paper, they'd think you were a bit odd, but anyway. Okay, here we are. We've got the same sort. Look at this chemical test that carried out between these two. Well, this one here is an alkyne. I'm sure you remember that. This thing here, no double bonds, no triple bonds. This is an alkane. So I think you know how we're going to do that. That's really very simple indeed. This is this one again. Okay, so that one's going to react with that and not with this. Now, we've got a chemical X, and X is mixed with bromine water and it remains yellow or orange, doesn't matter. Then they got some more, another portion, some more of X reacted with potassium dichromate. Now, potassium dichromate, just if you're not sure, in an exam, just remind yourself, oh, that's an oxidizing agent. Okay, if it remains yellow, that means it's not an alkene. The color goes from orange to green. Yes, okay, so this has been oxidized. What conclusion can be made from the bromine water? Okay, it's not an alkene. The acidified potassium dichromate, it's quite important that you say that you understand that what's happened. It is oxidized. Okay. Now, if it's oxidized, that means that it's turned into something else. And then it says solution X was reacted with a piece of metal and a colorless gas was produced. Describe a simple experiment to identify the gas. The difficulty is just spotting the thing that it says in the question. It says a piece of metal. Now, the only things that generally are formed when you get a piece of metal reacting with something is hydrogen, okay? Because the metal kicks out the hydrogen out of alkanols and alkanoic acids. Let's assume for a minute it's an alkanoic acid. So alkanoic acids are ROH, and a piece of metal like sodium will kick out the hydrogen here and we'll get RONA and hydrogen. We'd have to balance it by having twice of everything, but that's it. Now, it says, describe a simple experiment to identify the test, the gas. What test is that? Basically, it is collect, that's important, the gas and try to light it. So you could, oh, don't do that, don't be silly. You could say with a match or a splint or whatever you want to call it, it would burn with we often call it a squeaky pop, but it's a pop, okay? It burns with a squeaky pop, that's it. Collect the gas, try to light it. Those are the points for that, okay? All right, getting towards the end here. This is about synthesis. That's turning one chemical into another one. And this is one that we've seen and this is one that you've already got. What I want to point out here is how you start this. So I start with, okay, ethanol here. I've got glucose here. So if I go, oh, what's happening here? Why can't I draw? Good. So I want to draw. So I'm going to start here. I'm going to go, okay, come on. Oh, how very peculiar. Oh, for some reason, I don't seem to be able to draw on this one. Anyway, what I'm going to, I'll just talk you through it. What I want you to do is I want you to start thinking, okay, if I start with any particular chemical here, all right, as I start here, I want to concentrate on what happens between glucose and ethanol. Ah, yeah, okay. Glucose to ethanol. Then when I look here, I'm starting at crude ethanol to pure. So I'm looking at what changes each time. Glucose to ethanol, crude ethanol to pure ethanol. Glucose to ethanol, that's fermentation. From crude to pure, that's fractional distillation. This is an oxidizing agent. If I take ethanol and I oxidize it, I produce ethanoic acid, alkanol, alkanoic acid. Acids react with sodium to produce hydrogen and the salt. So that will be sodium ethanoate. If I add ethanol, this is on your map, your organic map. If I add ethanol to the alkanoic acid, then, and the little bits of the catalyst, concentrated sulfuric acid and warm, then I'm going to get the ester. That's ethyl ethanoate. If I go back to here and I look ethanol and I heat it with concentrated sulfuric acid, this is going to dehydrate it. This is a dehydration. If I take H and OH out of that, that's taking water, H and OH, I produce an alkene. If I take an alkene and I put it through process M, that will produce the alkane, okay? Now, that would be hydrogenation with hydrogen, nickel, and so on. Now, that allows you to answer all the questions below, all these ones down here, until you get down to, yes, this one here. Write an equation for the reaction of B and sodium metal to form substances W and V. Let's see if I can write now. So I've got B is, oh, I can't. Okay, that's odd. I'll see if I can write it right at the bottom. Yes. So that is, let's make it a bit finer than that. So that is F, oh, Lord, too big. Just get rid of that. Ugly. Okay. So ethanoic acid is this. When I add sodium to it, the sodium kicks out the hydrogen. It always does, not these ones. These ones never change. So we get CH3, COONA, and hydrogen. We should balance it. This would be just one H. So we'll have to balance it like this. Okay. This one here with bromine water added to a sample of A, if you go back up to A, bromine water with A, here's A. This is the dehydration, starting with, oh, it's writing now, how very peculiar. That takes water out of it. Now it takes one H and, sorry, two H's and one O, and that will leave C2H4. That will tell us that that is the alkene. This is ethane, oh, and therefore this must be the hydrogen and nickel and 70 degrees Celsius. Okay, we've dealt with this one. This is ethanol going to ethanoic acid, alkanoic acid, and this going to here, which is CH3, COO, C2H5. I wonder why it suddenly started writing. What I wanted to say up here was, when you try to concentrate on a process, try to concentrate on, this is going from glucose to ethanol. And then in the next bit, I'm looking from crude to pure. And in the next bit, I'm looking for ethanol to something else. In other words, I'm trying to concentrate on just one thing at a time. Ethanol to B and so on. Okay, so I'm looking at what actually affects the change, what makes the change happen. Okay, yeah, does that make sense? So I try to concentrate on just one bit at a time. I hope that's useful. I'm back here. Your supervisors will have all these answers. I hope that will make life a bit easier when you can go through and just listen to them and work out how it goes. Okay. God bless you. Good luck.